Example 6. Suppose a bowl contains 10 golf balls of the following colors: 5 red, 3 white, and 2 blue. If 3 balls are randomly drawn from the bowl without replacement, what is the probability that all 3 balls will be white? What is the probability that none of the 3 balls will be white? So this is our rule that we were looking at on the previous video, except we're extending it. We're extending it into a third scenario. So if we want to know the probability that all 3 balls are white, then that's going to be the probability that the first ball is white times the probability that the second ball is white, given that the first ball is white, times the probability that the third ball is white, given that the first 2 balls are white. So the probability that all 3 balls are white is going to, again, equal the probability that the first ball is white, which will be 3 out of 10. Now, this is without replacement. So the probability that the second ball will be white, given that the first ball was white, means there's only 2 white balls left in the bowl out of 9 balls left in the bowl. So the probability that the second ball will be white will be 2 out of 9 if the first ball is white. And then what's the probability the third ball will be white? Well, that will be 1 out of 8. If the first 2 balls are white, then there's only 1 white ball left in the bowl, and there's only 8 balls left in the bowl. So 3 out of 10 times 2 out of 9 times 1 out of 8 is going to be our probability. So if we do this, 3 out of 10 times 2 out of 9 times 1 out of 8, that is a 0.008 probability. So this probability is approximately 0.008, 8 thousandths. Now, what is the probability that none of the 3 balls will be white? So, probability that none are white. Well, that will be the probability that the first ball's not white times the probability that the second ball's not white, assuming that the first ball's not white, times the probability that the third ball's not white, assuming that the first 2 are not white. Well, there are 3 white balls, there are 5 red balls and 2 blue balls, so there are 7 balls that are not white. So when I draw out the first ball, the probability that that first ball will not be white is 7 out of 10. Now, assuming that first ball is not white, that means there would be only 6 non-whites left out of 9 balls for the second. And if I draw out the third ball, there will only be 5 non-white balls left out of 8 balls left in the bowl. So 7 out of 10 times 6 out of 9 times 5 out of 8. So 7 out of 10 times 6 out of 9 times 5 out of 8, that probability is about 0.292 if I round to 3 places. So 0.292 is the probability. So pretty likely, if I draw 3 balls out of the bowl, that none of them will be white. Using tree diagrams to calculate probabilities. We can represent an experiment that happens in stages with a tree diagram whose branches represent the outcomes of the experiment. We calculate the probability of an outcome by multiplying the probabilities found along the branches representing the outcome. We call these tree diagrams probability trees. So the idea here is that we can use a probability tree to help us determine probabilities. So let's take a look at an example to help make sense of this. Example 7. John is participating in a lottery for a campus parking space. Lot A holds 40% of the campus parking spaces, and Lot B holds the other 60% of parking spaces. So John's either going to get a space in Lot A or a space in Lot B. Also, 20% of the spaces in Lot A are covered spaces, and 30% of the spaces in Lot B are covered spaces. So there's some kind of covering to protect the car from weather, let's say. So question A, we want to draw a probability tree to visualize this situation. So if we think about John's outcomes here, he could either end up in Lot A or he could end up in Lot B. And if he ends up in Lot A, he could either end up in a covered parking space or an uncovered parking space. And if he ends up in Lot B, he could either end up in a covered parking space or he could end up in an uncovered parking space. So he could either end up in A covered, A uncovered, B covered, or B uncovered. Now we can use the tree diagram to help us determine the probabilities of the different outcomes. So in this case, John has 4 possible outcomes. He could end up in A covered, A uncovered, B covered, or B uncovered. That's the idea. So the probability of ending up in Lot A is going to be 40% or 0.40. That's the probability that John's going to end up in Lot A. And the probability John's going to end up in Lot B is 0.60. Now, if John ends up in Lot A, the probability that he's going to end up in a covered space is 20%, or 0.20. So the probability of ending up in covered is 0.20. 0.20, not 0.02, 0.20. And the probability then that he ends up in an uncovered space is going to be 0.80. If John ends up in Lot B, the probability that he's going to end up in a covered space is going to be 30%, or 0.30. So if John is in Lot B, the probability that he's going to be in a covered parking spot is 0.30. The probability he'll be in an uncovered parking spot will be 0.70, the complement. So the idea here is if I follow this tree, the probability that John ends up in A and covered is going to equal the 0.40 times the 0.20. Now 0.40 times 0.20 is 0.08. So this probability is 0.08. The probability that John ends up in Lot A and uncovered, so A and uncovered, is going to equal 0.40 times 0.80. So 0.40 times 0.80, that is equal to 0.32. The probability that John's going to end up in Lot B and covered is going to equal 0.60 times 0.30. Well, 0.60 times 0.30 is 0.18. And the probability that John ends up in Lot B and uncovered, so the probability of B and uncovered is going to equal 0.60 times 0.70. 0.60 times 0.70 is 0.42. Now this is our probability model. This is all of the possibilities. A uncovered, 0.08 probability. A and uncovered, 0.32 probability. B uncovered, 0.18 probability. B and uncovered, 0.42 probability. So this is our probability model. If we add those up, that adds up to 1. So question B. What is the probability that John will receive a covered parking space? So we want to know what's the probability he ends up in a covered space. Well, it's a little bit tricky because there's two different ways he could end up in a covered space. John could end up in A covered, or John could end up in B covered. So the probability that he ends up in A covered is 0.08. The probability he ends up in B covered is 0.18. So the probability that he ends up in a covered space is going to be those two things added together. So that's again going to be the probability that he ends up in A and covered plus the probability that he ends up in B and covered. So that's going to equal 0.08 plus 0.18. And if we add those together, 0.08 plus 0.18, that is 0.26. So John has a 0.26 probability of ending up in a covered space in this lottery for campus parking spaces. So we have one last concept to discuss, and that is the concept of independence versus dependence. Events E and F are independent events if the probability of F given E equals the probability of F. E and F are dependent events if the probability of F given E does not equal the probability of F. So we have two examples that deal with this concept of independence versus dependence. So take a look at example 8. Suppose one card is drawn from a standard 52 card deck. Are the events the card is a king and the card is black independent or dependent? So if we think of the card as a king as event E, and if we think of the card is black as event F, then what we want to check is, does the probability of F given E, does that equal the probability of F? So are these two probabilities the same? In other words, if I find what's the probability the card is black, given that it's a king, does that equal the probability that the card is black? I'm going to just write black. So is the probability of black given king equal the probability of black? Well, let's think about our cards. So here's our deck of cards again. And so if we're given that we have a king, then there are 4 kings. And of those 4 kings, 2 of the kings are black. So the probability that the card is black, given that it's a king, is going to equal 2 out of 4, or that simplifies to 1/2 or 0.5. Now the probability of being black, well, there are 52 cards and 26 of those cards are black. The probability of being black is 26 out of 52, which reduces to 1/2. So the probability of F given E equals the probability of F. They both equal 1/2. So in this case, we have independence. So the event, the card is a king and the card is black, are independent because we got the same probability. The probability of F given E equaled the probability of F. That is, the probability that the card is black, given that we have a king, equals the probability that the card is black. Let's take a look at example 9. Example 9 says, look back at example 2. Are the events excellent health and very happy independent or dependent? Now what we're going to look at here is the table of data that we had back in example 2, but I want to think about this before I draw back in that table. So excellent health and very happy. So again, this is like E and this is like F. So I want to check, is the probability of F given E equal to the probability of F or not? Are they different? Well, the probability of F given E, that means the probability of very happy given that they're in excellent health. So does that equal the probability of very happy? This is what we're looking for. Well, if I pull back in this data, now again, we're looking for the probability of very happy given excellent health. So if we're given excellent health, there were 11,022 individuals in that category, and 5,095 of them are very happy. So that probability is 5,095 out of the 11,022. So if I change that to a decimal, 5,095 divided by 11,022, that is 0.462 if I round to 3 places. So 0.462 is, again, the probability of very happy given that the individual's in excellent health. So now what is the probability of very happy? Well, now here there's no given. So the probability of being very happy, well, altogether there's 11,347 individuals who are very happy out of 35,394. So this probability is 11,347 because there were that many individuals who were very happy out of 35,394 because there were that many individuals altogether in this data. So if I take 11,347 divided by 35,394, do I get the same result or do I get a different result? Well, if I round to 3 places, that is 0.321. So 0.321. So the probability of being very happy, given that they're in excellent health, is different from the probability of being very happy in general. So because these are not the same probability, that means these two events, excellent health and very happy, are dependent. So again, if the two probabilities come up to be the same, then the two events are independent, as in example 8. But if the two probabilities aren't the same, then the two events are dependent. That concludes this video. At this point, you should now be able to handle the section 13.3 homework.